No, and that's, so there's kind of three things that you need to make a good treatment with a radioisotope. So you need to have the isotope itself, and it's got to have the right properties, it's got to have the right half-life, it's got to have the right type of decay. But you can't just stick an isotope in somebody because it won't go where you want it, right? Free isotopes in the body are very bad. So you have to have that, what we call a chelating agent. So you've got to have a way to hold that isotope tightly. It's not going to come out, and having things in the body is chemically very, very challenging. And then you have to have a targeting moiety. So usually that's a peptide or an antibody. And so you've got to have those three pieces all together in a way that's going to work. So right now for actinium, there are several antibody-based drugs that target different sorts of cancers, and they're going after gliomas and lymphomas are sort of the targets that they're looking at right now. But I think, as a researcher, looking at new targeting mechanisms there's just so much work to be done, and it's so important. So what we do in the isotope program is really focused on the front end of supplying that right isotope. And so we have collaborations in academia where we're trying to look at the next two pieces. How can we hold that isotope, and then how can we get it where it needs to go in the body?
If you can make enough of it, that will motivate a lot of research.
Right, because if they don't have any to work with, then yeah, they're not going to pursue that. So it's the critical first step, but it's definitely not the last step.
How are these isotopes transported?
So shipping is very challenging. So I have a friend in the back who helps me with all our sorts of shipping issues. So we use certified containers. If you have up to certain amounts of radioactivity, they're called type A containers. And so those have to go through certain amounts of testing. And so our normal type A container has a small lead shield. It's about this big, and it sits inside a larger lead-lined box. And so one of those boxes weighs about 50 pounds, and amazingly enough, it can go on a FedEx truck. And so,
there you go.
Wow. So that's actually how we ship most of our isotope. And so as long as you keep below the thresholds, the allowed thresholds for those containers, you can ship by FedEx, by air. If you go to larger quantities, it gets even more challenging. And then they have what they call type B containers. Those are very heavily regulated. We own one in the isotope program because we have to use it to ship our targets from the plants over to the processing facility. And so that container, it weighs 8,600 pounds. It's about this big around and this tall. The paperwork that governs the regulations for that is a binder about that thick. And so it's regulatory difficult, but you're shipping very, very hazardous things, so it needs to be safe.
So air shipping is used on the other?
Not for the 8,600 pounder
No,
on the
but-
truck,
but-
but
but
for the smaller ones, yes, absolutely. And for us, it's very important because you have these short-lived isotopes. You can't afford to truck them around, so you can't afford the time. So these containers are very, very safe. They go through rigorous testing.
So when you hear about a FedEx plane going down,
Yeah.
you
It could be in there.
worry a little.
Well, I think those little lead shields would probably be just fine. So yeah.
So Eva,
Yeah.
so has there been a case in the past of a plane or a FedEx truck actually emitting any radioactivity from one of those cases?
And not that I'm aware of. I mean, I could probably can get Dawn to weigh in the bag. I mean, like I say, they're very heavily regulated. They track everything really, really well. When we ship isotopes out, we actually have 2 people just in our team that are dedicated to shipping. So not only do they do all the paperwork and make sure that we've dotted our I's and crossed our T's, that we've done all the quality assurance work, but they monitor that and make sure it gets right to where it's supposed to be.
So I'm always interested to learn about what's going on in materials science and the interesting things that the Center for Integrated Nanotechnologies is doing in learning about how materials actually work and behave. Are you working with anybody in that field on your targets? Because you said, boy, if you could make them more robust, you could actually do some more really good work.
Yeah, so one area where we have collaborated with material science people has actually not been on the targetry side, but on a basic science application. And so for long-term radioactive waste storage, people are interested about making salt forms and looking at their stability over very long periods of time. And so we've used some of our isotopes to grow crystals, and then you can study these physical transformations in the crystals on very short time frames. So things that would hopefully mimic what would happen in a multi-thousand-year aging process, and you can look at them on a much shorter time frame. And so you can force some really interesting chemistries, because when something decays, it turns from one element to another. And so suddenly that crystal structure is really unhappy and perturbed, and interesting things happen on a very tiny scale. So that's been one area where we've had some really interesting basic fundamental science interactions.
Cool.
Yeah.
Can, or maybe it is already, the process can be automated with robots fully, perhaps?
Yeah, we keep talking about that because we rely so much on our operators to do everything. And to work with the remote manipulator arms is really difficult. But the flip side of that is the hot cells, they're there for a reason. The radioactive fields inside those hot cells are very high, and so electronics don't survive. They're corrosive environments because of some of the acids and things that we use. So we keep talking about it, but we haven't really made a lot of progress in that area. If you look at commercial radioactive, like fluorine-18 is a very short-lived isotope that's made in small cyclotrons that sit next to hospitals. Those are fully automated, and that's really amazing, slick stuff. So we hope to translate some of that sort of research into our applications, but we haven't really done it yet.
If it's safe for the operator, it must be safe for the robot to handle the.
But the operator's outside, right? So
Right.
if you keep the electronics on the outside,
Yeah.
yes, you could certainly come up with
Okay.
ways of doing it. So I think there's opportunity there that we could tap into that haven't yet.
We spoke of the FedEx accidents. Have there been accidents around the hot cell, or through the whole process?
So we work very, very hard
Right.
to make sure that our people are safe,
Right.
absolutely. And so when we've certainly had accidents and things happen,
Right.
but I would put them more on the scale where they've made big messes that we have to clean up, not that people are getting exposed or injured. And so we worked, with the remote handling to make sure that the consequence of error is
Right.
is low. So I've been with the program for almost 7 years now, and so in that time we've had a few skin contaminations, usually involved with shipping or maintenance activities, but these are things where you wash it off and there's no long-term consequence. We haven't had any real accidents, and we work very hard to make sure that's the case.
I've got a funny story about radioactive isotopes.
Funny story.
My doctor told me I had to take a stress test, and so they filled me with, I think it was thallium, radioactive thallium.
Thallium-201.
Half-life is 10 days or something like that. Well, I was working at Lance at the time. You probably know where I'm going with this now. I went in the next day, and that was fine. And I came out that evening, and I have a very sensitive detector there. And all hell broke loose.
Yeah.
Bells, whistles, alarms. So I told the security guy what happened. He said, well, just give me a call. Well, the next week, I forgot.
Uh-oh.
And I went through it again, and this time there was a PTLA guy there. And all hell broke loose, and he comes running after me. He's unclipping his holster and pulling out his gun. I'm thinking, I don't need this.
Not good for your stress.
Yeah, right.
Yeah.
That is funny.
Yeah, so the detectors and as you know around the lab are set so low that we can't, if we had any small incident, we'd be caught so fast. So people are routinely given with radioactive procedures is actually much higher than what I would be allowed to work with on the bench. So it's kind of interesting. So the strontium-82, so here's another why I love strontium story. The actual active agent is the daughter. It's rubidium-82, which has a 75-second half-life. And so obviously you can't package it or ship it anywhere. It has to be generated at the point of care. But that's why it's so great, because by the time the patient, they're literally injected as they're sitting on the PET scanner. By the time they get out and they walk out the door, there's nothing left. It's all decayed. And so you get really sharp images, and the dosimetry, the exposure to the patient is really low. So you know, finding isotopes like that, that's great.
So you talked a little bit about like cyclotrons. Can you talk a little bit more about how you can produce isotopes other than how you would do that way, or how it's different?
Sure, yeah. So the main two ways are with charged particle irradiation, so using protons, using deuterons, so you can use different sorts of accelerators to impact on materials and make isotopes. The energy range that you use changes what parts of that chart of the nuclides you can access, but we can only essentially get to half because we're using charged particles. So the other way to do it is to irradiate with neutrons. And so reactors make very different sorts of isotopes than what we're capable of making. And so Moly-99, Tech-99, we can't make that here. And so people are very concerned about the long-term shortages of Moly-99. That's not a problem that at least the isotope program can contribute to. So you can try and look at other ways to do neutron-based reactions. But those are really your two main ways of producing things. You can use high-energy electrons as well, but that's much less well studied and less understood. But you basically, you know, you've got to have enough energy to knock some sort of particle out of a nucleus so that you can access something that's not stable. Yeah.
You said that it was the strontium that's used in the imaging, and that it's decayed into rubidium, which uses like 75-second half-life for the imaging. What is the actual catalyst for that reaction at the point of care?
So the strontium-82 is used in a generator. So it's a 25-day half-life isotope. It's immobilized on a solid support, a titanium oxide column. The rubidium-82 doesn't stick on that column, and so they push saline through, and the rubidium-82 just comes off. And they use a sterile saline solution, and so it's directly injected into the patient from that generator. And the only reason that works in this case is because it doesn't, it's one very simple case. You don't have to have the chelator or the directing agent like I talked about for the actinium. It's because rubidium is right below potassium in the periodic table. It's a simple salt, so it behaves very much the same, and it goes to the potassium ion channels in the heart. And so it's very, very good for imaging those heart muscles, but applying that to some other thing would be very, very hard. Does that help?
Yes, and the follow-up question to that, that's the technique that was milking the cow, right?
Yes.
Okay.
So anytime you have usually a longer-lived parent isotope and you are interested in using the daughter, a very short-lived daughter, you set up that sort of apparatus. Now there are some times when you can milk the cow and you can use the daughter for synthesis and making a secondary drug. So actinium-225 actually has a 45-minute half-life daughter, bismuth-213. And so some of the drug applications are based on the bismuth because the chemistry is better understood. And so there's lots of different ways to sort of slice this pie of applications.
Wow.
Mentioning the bismuth, that's one of my favorite crystals. Having it be such a unstable compound, does it have any of the properties of the normal non-isotope element?
Yeah, so from a chemistry standpoint, it's identical. You usually just don't have enough of it around to do the same sorts of things with it. So when you have a radioactive element like that, it's oftentimes in such small quantities that it doesn't behave like the bulk material. And so that can make the chemistry sometimes challenging because you may have developed something with stable bismuth, but then you go try it on your really, really, really dilute solution of radioactive bismuth and it doesn't work the same. And so these large concentration changes can really impact the chemistry and make it more challenging. So you can try and mock things up and study using your stable elements, but sometimes the translation doesn't always go like you hope.
In the world, either in production or in coming in online, are there other places like this that also produce in the world? China, Europe?
So there are not very many high energy machines like we have. So there are thousands actually of low energy cyclotrons, and they can make certain things. So around the world for
Right.
sure. But for very high energy machines like what we have that can make strontium or actinium, there's Los Alamos, there's Brookhaven, there's the Triumph facility in Canada, there's the Institute for Nuclear Research in Russia, and we actually get irradiated targets from them and we process them. That's a fascinating collaboration. There's the Ithembo facility in South Africa, and there's a new facility that's coming online in South Korea. And that's, I don't think I forgot any, that's pretty much it for high energy machines like that. There are certainly other machines that can achieve those high energies, but not at the sorts of currents that you need for bulk production.
So to follow that up, because you need such tremendous amounts of energy, there has to be sort of a minimum energy requirement for radiation medicine, right? Like, so does that mean that being able to install or produce or construct one of those linear accelerators is largely contingent on that region's ability to produce that amount of power?
So, you're asking like about electrical power to supply the LINAC?
Right.
Yeah, so it is significant, but that's not a showstopper. It's really the financial investment. So to build a big machine like that is just a tremendous financial effort. And so really all of those that I just named are government funded. And so to build a big accelerator like that, no one has privately taken that on yet. So you've got to have lots of drivers, and isotope production would only be one of them. Usually those are facilities that do lots of different sorts of research and serve other purposes as well.
So did we start doing this when Louis Rosen and LAMP was created, or what's our history of doing this? How
What's our
long have we been
history?
doing this?
So we have been making isotopes since the late 70s. So LANS was commissioned in 1972, and we used to accelerate protons all the way to 800 MeV. And so that's the end of the beamline at LAMS. And so isotope production at 800 MeV is actually very different than isotope production at 100 MeV. And so one of the reasons is now you're talking so much energy that when you hit things, you really